Welcome to this explainer. Have you ever stopped to wonder how scientists actually measure and separate microscopic, totally invisible polymers hidden inside everyday commercial products? I mean, from the plastics in our devices to the food in our pantries, figuring out the exact chemical makeup of these materials is absolutely crucial. So let's dive right in, because today we're demystifying a seriously powerful technique called size exclusion chromatography, or SEC for short.
Here's our roadmap for today. We'll start with a welcome to size exclusion. Then we'll look at weighing invisible polymers, mapping the calibration curve, exploring real-world chemical analyses, and finally, checking out chemistry on the web.
All right, part one, welcome to size exclusion.
There's a brilliant, almost counterintuitive aha moment when you compare SEC to standard filtration. Now, the source material points out that gel filtration, which is just what we call SEC when the mobile phase is aqueous, must not be confused with normal filtration. Think about your morning coffee filter, right? In normal filtration, the biggest particles get trapped and the tiny liquid molecules flow straight through. But SEC actually produces the exact inverse phenomenon. It's wild. In SEC, the stationary phase is made of a material full of tiny pores. As the sample flows through, the small molecules get completely sidetracked. They wander into these pores and take a much longer winding path. The biggest molecules, on the other hand, are just too large. They're entirely excluded from the pores, so they bypass the whole maze and flow right out of the column first. Basically, the biggest flow through while the smallest get retained.
Moving on to part two, weighing invisible polymers.
Now that we understand how these molecules flow and get separated by size, we need to nail down what we actually mean when we talk about a polymer's weight. Here's the kicker, and it's a concept that trips up a lot of people. When we think of a pure substance, we usually imagine a single uniform identity. But a polymer, even in its absolutely pure state, isn't just one uniform mass. Nope, it actually corresponds to a whole distribution of macromolecules with different masses. Think of it like this. Some chains are a little longer, some are a bit shorter. So we're not just hunting for one single number. We're looking for a distribution of molecular weights to find the mean mass and the most probable mass. And SEC is literally the perfect tool to determine this distribution.
Okay, let's hit part three, the calibration curve.
So how do we actually translate the time it takes for a molecule to flow through a column into a real physical mass? Well, the plot we use brilliantly illustrates the solution. To figure out the mass of an unknown sample, chemists create a calibration curve using standard macromolecules with known masses. They plot the retention time, or volume, on the horizontal axis against the logarithms of the molecular masses on the vertical axis. And as you can see, this creates a beautiful linear relationship. It forms a perfectly straight line over a really wide range of masses, which, by the way, is often achieved by mixing different stationary phases together.
Breaking that down, you just follow four straightforward steps. First, you run your known standards through the SEC column. Second, you plot their retention time against the log of their mass. Third, you identify that linear relationship. And finally, step 4, when you run your unknown sample, you simply find its retention time, go up to your line, and read across to find its approximate mass. The big underlying assumption making this whole thing work is that the mass of the molecule and its molecular volume are directly related. It's just a highly elegant analytical solution. Next up, part 4, real-world chemical analyses.
Let's see how this builds from abstract math into tangible, real-world applications. Because chemistry isn't just done in textbooks, right? It's used to guarantee the quality of the world around us. When we look at real-world separation side by side, you really see the versatility of the method. On one side, we've got the separation of synthetic organic compounds, like polymer plastifiers, using gel permeation. But SES isn't just for lab plastics. Look over to the other side. It's incredibly effective at separating mixtures in everyday items, too. You can see the precise separation of glucose oligomers in everyday corn syrup, and right next to that, the separation of a peptide mixture.
These aren't just academic exercises either. SEC is a super useful technique for the control analysis of commercial samples with totally unknown compositions. Oftentimes, commercial products contain a mix of large polymers and small molecules. Now, for typical organic compounds, you'd probably use techniques like HPLC or gas chromatography, but for sugars and polysaccharides, SEC is absolutely the go-to. These control analyses are essential for guaranteeing the quality of the stuff you interact with every single day. We're talking about the starch in your pantry, the paper pulp used to make the pages on your desk, and literally countless food products and beverages. It's invisible science protecting everyday quality.
Finally, part 5, chemistry on the web.
You know, the analytical instruments are only half the battle. The other half is information. As our source material points out, info on different types of chemical analysis can easily be found on the internet, which serves as a constantly updating goldmine. It offers everything from vast spectral databanks to physical chemical constants and application notes. You can download the analytical software you need to process those complex chromatograms we just looked at. Plus, you can connect directly to university databases, like the chemistry sites at the University of Sheffield, or just shoot a direct email to leading specialists around the globe. This user-friendly system allows for the immediate transmission of documents and collaborative problem-solving that was literally impossible just a few decades ago.
And that brings us to the end of our journey today. We've seen how size exclusion chromatography cleverly uses microscopic pores to sort molecules from biggest to smallest. We've learned how chemists use logarithmic calibration curves to translate flow time into exact molecular weights. And we've seen how this guarantees the quality of everything from synthetic plastics to the corn syrup in your kitchen. So think about how you might combine these incredibly powerful digital tools and analytical techniques in your own scientific journey. Armed with endless digital databanks and the power of size exclusion chromatography, what invisible chemical mystery will you solve next? Thanks for joining me on this explainer, and keep learning.